here. As usual, we will start with a quick refresher. Last week, we explored dynamic programming. We focused on the Fibonacci sequence. We first looked at the recursive implementation, and we saw actually how very, very slow it was. And this has led us to explore two dynamic programming techniques, which are memoization and tabulation. We also discussed the limitations of memoization as it uses a stack, which with high recursion depth, we run the risk of a stack overflow exception. And at the end, we summarized everything with a table to clarify the differences and the trade-offs. Well, now, building on that, today we are going to dive into greedy algorithms. Well, according to the Oxford English Dictionary, greedy means having excessive desire for something without considering the effect or damage done. And this concept is actually inspired by how we humans operate in our daily lives. For example, when things are under control, we often think we are multitasking and managing everything efficiently. But in reality, we are much like discrete functions or processors, just making decisions one step at a time. And every day we constantly face decisions like whether to spend more time at work or with family, or maybe to focus on building a better career or enjoying life. And in each situation, we simply make the best decision based on the current circumstances that we have. For example, if after having an amazing weekend with your family, you might decide to just work a little longer today. Yeah. Back to the greedy algorithms, well, they just work the same way. They don't think about the future. They pick the best available option right now, and they just don't care about the overall outcome. They just hope for the best. Yeah. Well, how did it all start? Well, the concept of greedy algorithm was defined or put in together by Etzka Dijkstra, who is a computer scientist and mathematician who wanted to calculate the minimum spanning tree, aka MST. So he introduced the term greedy algorithm, and it all just started from that. Well, since the greedy algorithm was at first designed for graphs, let's just explore an example for that and start with recalling a definition actually of a graph, which we saw in one of our previous sessions. Well, a graph is just simply a set of vertices and edges. And if we take that in one example to try to explore how greedy actually works, let's just see this. A graph has various keys, and you are to determine the maximum value in a tree. Well, a key is basically just the value of the node. For example, this root node has the key or the value 6. Yeah, an idea to approach this problem or solve it in a greedy way, we just think, okay, let's start by searching each node and checking its key to see if it's the largest value. And that's a valid way of thinking. And let's just see it step by step. Choosing this example, where we will start just with the root, mark it as visited, then check its two childs, which are the 3 and 4 in here. And we ask this question, which is bigger? Is it 3 or 4? Well, obviously it's 4, so we take it. And then we recursively apply the same logic. We check the childs of 4. They are 14 and 11, and we check which one is bigger. It's 14, so we choose the node with the key 14. And just like that, 14 has no child, so it's a leaf. So we are done with this algorithm. And at the end, we sum the values up, and we have 6 plus 4 plus 14, so we have 24. And yeah, let's check how efficient that was. And to answer this question, we will have to ask another question, which is, which tree do we have actually, because we will see later on that different trees which are the same data structure at the end leads to different time complexities. Well, as mentioned in the last session, a tree is just simply a special type of a graph, but today I will add a few characteristics on that, which are a balanced tree. And a balanced tree is just a tree such that its right and left subtrees' height differ by not more than 1. So if we check this tree, we will have that each node is actually balanced. And for example, this node has no kids, so we subtract 0 from 0 and we get 0. It's still within 1, so it's balanced. And if we check the 5, so it's 1 minus 0 kids. So it's 1 minus 0, it's 1, and therefore it's balanced. And even if we check the 4, we will have 2 minus 2, so it's 0, still within 1, so it's also balanced, and so on and so forth for all the other nodes. Another tree type, which is sadly not as nice as a balanced tree, which is skewed tree. Skewed is a term from linear algebra, which we use for matrices. We have symmetric matrices and skewed matrices, but whatever. Yeah. So as we see here, it's similar to a list actually. So it doesn't really have the form of a tree, but rather a list. And as we see, it has several non-balanced nodes, sorry. Because if we check this node with the value 4, we will see that 2 minus 0 is actually 2, bigger than 1, and therefore it's not balanced anymore. And even if we go higher and higher in the tree height, they are also not balanced. So yeah, different trees leads to different efficiencies. As we see here, the best case that we can have with a greedy algorithm is when we have a balanced tree, which gives us a time complexity of big O of log n. And in worst case, when we have a skewed tree, or the one that looks like a list, so its time complexity is big O of n. Oh, sorry. Yeah. And in both cases, actually, whether it's linear time, so big O of n, or logarithmic time, so big O of log n, both of them are actually pretty efficient. So that's nice. That's acceptable for a solution. But the question is, okay, the problem is solved and it's pretty efficient, whether it could be linear or logarithmic, but is it really the biggest value that we can get from this tree? And the answer to that question is no, because there are other branches and other values that we didn't compute, and they might give us bigger values. And an alternative approach could be exploring all the paths, then decide which one gives the best result. And if we apply this logic to our tree, we will start as usual with the root node with the value 6. And then we use backtracking or DFS, and therefore we will start with the leftmost branches. So we take the 3, then explore as usual the leftmost branch. So it's 20. 20 is a leaf, so we cannot explore any further nodes. So we stop there and we add the values together. We have 6 plus 3 plus 20, and it's actually 29. And we already have a bigger value than the one we found earlier. But are we done yet? We are not, because there are other branches that we didn't explore yet. So we explore the right branch now for the node with the value 6. So it's the 4. And then we check, as usual, the leftmost branch first. So we check the 14. 14 is a leaf, so we stop there. We sum them up. We have 6 plus 4 plus 14. So it's 24. And it's just the one that we had last time, but this backtracking or DFS algorithm checks all the branches. That's why we are recalculating them. Are we done? No. We have another branch, which is the right one from the side of the node with the value 4. So it's 11. 11 is a leaf, so we stop there. and we add the values all together, and we have 6 plus 4 plus 11, so it's 21. At the end, this algorithm compares all the values that he had from the different paths that he visited, and we get that 29 using the leftmost branches is the most optimal one and gives me the biggest value. So it just returns 29 and returns the corresponding nodes for giving this value. Now, how efficient this backtracking or DFS? Well, we are its time complexity is big O of n, because we are simply just exploring each node once. If you just remember what we did, we explore all the branches, which means each node is visited one time, and that's also the same logic of the DFS. So at the end, with whether the tree is balanced or it's a skewed tree or a random tree, at the end we will have a time complexity of big O of n, and which is slower or similar to a greedy algorithm. Yeah, so the greedy algorithm, its traversal type was just using one path, and it always picks the highest value child. With backtracking or DFS, we explore all the paths and all the nodes, then we return the biggest or the highest value, or the thing that we are looking for. About time complexity, it's greedy gives big O of log n if the tree is balanced, or it gives big O of n if it's a skewed tree or non-balanced tree. With backtracking, we have big O of n. And does greedy guarantees optimal solution? The answer is obviously not, because we have seen that greedy gave us 24 and backtracking gave us 29, so it's not optimal and it's not the result that I was aiming for. So yeah, because it just misses a better path. So which might better paths which could be leading to better results. And backtracking, yes, it always finds the optimal path, since it explores all of them and then decides based on the results it has. Yeah. Well, key differences between both of them. Greedy is fast, or as fast as backtracking, but it misses the globally best path, since it just focuses on the locally optimal one. And backtracking checks all the possible paths, so it always finds the optimal path, but it is slower. Now, yeah, we are again confused and we have to make a decision. Should I use greedy or backtracking or DFS or dynamic programming? What is more important? Is it writing faster code or a correct one that gives me the optimal result that I am looking for? Well, I would simply advise you to use greedy in situations where it gives you the fastest and the correct solution as well. Where is that? Well, there are some real-life applications where greedy works best, which are, first of all, the Huffman coding or the data compression. It's used in the zip compression or GPAG and MP3. Why greedy works here? Simply because the Huffman coding builds an optimal prefix tree by greedily choosing the least frequent characters first, ensuring minimal encoding path. So actually, the whole problem resolution is based on greedily solving the problem, and that's why a greedy approach is the one to use in data compression. Yeah. Else, of course, Dijkstra developed the whole greedy approach. Therefore, there is an algorithm that's named after him, which is Dijkstra algorithm, and we spoke about it when we have seen graphs, the weighted ones, and we have seen that if we want to check the shortest optimal path with weighted graphs, then the Dijkstra algorithm is the best one, and it's used in Google Maps or GPS navigation, but also with internet routing protocols, so when transferring packets in the internet. And why it works? Well, it simply always expands the least cost path first, ensuring the shortest path from the source to all the other nodes in a weighted graph. Another real-life application is activity selection problem or scheduling tasks, which is used in scheduling interviews or also in your computer with the CPU task scheduling. Why it works? Well, because selecting the task that finishes the earliest maximizes the number of tasks that can be scheduled. For example, if in this graph, when I have these several activities with its corresponding needed time to be done, so probably I will start with A3, then A6, then A1, then randomly choose A2, A4, or A5, since they have all same mix span. Yeah. Last but not least, also greedy algorithms are used in the coin change problem. So basically in the ATM cash withdrawal or in the vending machines. And why it works here? Because always picking the highest coin value ensures the minimal coins. So if you give me 29 cents and you want me to, for example, change them in from euros to dollars, or just give you for example, if you have $50 and you want to have five coins of $10 or whatever, so changing coins works very efficiently with greedy algorithm. And when not to use it, when it's not really nice to implement the greedy algorithm. Well, basically, when a problem has dependencies between choices, what does that mean and what's its application? Well, one of these applications is finding the largest sum path in a tree, just like we saw earlier when we wanted to find the largest sum path in the tree that we had, and the greedy algorithm gave us 24, I guess, but a dynamic programming or the backtracking approach gave us 29, which is bigger and which is the value that we are aiming for. So in such problems, greedy fails because greedy algorithm only looks at the immediate next step, choosing the child with the highest value at each step. And however, a locally optimal choice may lead to a sub-optimal total sum if a better path exists elsewhere in a tree. And just in the example that we saw, we had, I guess, 29, 24, and 21. And 24 is the result that we had with the greedy approach, which is the suboptimal total sum. So it's just like almost the median one, magically. Yeah. And a real-life example of this is imagine you're driving from city A to city B and only taking roads with the highest speed limit at every turn. You might end up taking longer detours instead of slightly slower but shorter and more direct route. Well, a better approach could be backtracking or dynamic programming to explore all the possible paths to ensure the best total sum, or just use Google Maps. It will give you at the end the best routing path that you should use, and it works actually with dynamic programming. Second, you can't really use greedy algorithms with problems where the optimal choice isn't clear from the local decisions. For example, the knapsack problem. A greedy approach might select items based solely on their value to weight ratio, which could fill the knapsack with items that prevent the inclusion of an optimal combination of items. And a real life analogy for that could be when you are packing your suitcase with items, choosing the item that seems more valuable or important first might leave not room for a combination of items that would overall have better serve for your needs for the trip. For example, you start with packing, I don't know, your laptop, your fancy clothes, so you can make nice selfies in the country you're traveling for, but then you forget, for example, some papers that you should include, or some important things, or for example, the traveling application that this city is using for its mean of transportations. A greedy algorithm is also not optimal for problems when exploring our possibilities is necessary. For example, the traveling salesman problem, aka STP. A greedy STP algorithm typically chooses the nearest and visited city at every step. While this might seem logical, it can easily result in suboptimal tours, and also the algorithm might lock into a path that forces long detours later. And a real-world analogy to that, just consider a delivery route where the driver always heads to the closest next drop-off. This might seem efficient initially, but would force the driver into a situation where they have to cover large distance to reach the remaining destinations, and which at the end increases the overall travel time. So yeah, final thoughts that you should take with: greedy algorithms are powerful and efficient when local decisions guarantee global optimality, and when dependencies between choices are minimal. So, and when greedy is not suitable, when the problem requires balancing short-term gains with long-term benefits, and also when each decision has sequences that affect the subsequent choices, just like the example we saw, that in order to find the max value, it does not just depend on the maximum between the child of the node, but either on the overall maximum value that we summed up in each branch. Also, it's not suitable when exploring all the possible combinations is necessary to ensure the best outcome. Just like we saw in the time scheduling, we have to see all the possible combinations of all the tasks and take their total make span into consideration. So at the end, we have the most optimal scheduling table. And this was short and brief. Next, we will explore divide and conquer, which we kind of also saw in the sorting session when we spoke about the merging sort, and there we explored the divide and conquer technique that's running behind the scenes of merging sort. But next week, we will try to apply it onto other problems and see how it's really used. And also, since next week is the last session as well, I will try to summarize all the things that we have seen. And basically, I will also focus on each use case of dynamic programming, greedy algorithms, and divide and conquer. Well, thank you so much for paying attention. As usual, this is a QR code to connect with me. Now, if you have some questions, I have left 5 minutes for questions. It's your time to ask them. Yeah. I will stop sharing my screen.
I see just 2 questions, one from Aziz. Sorry, Ines, I have a question. Why do we use the greedy when dynamic always works? But it was at the start of your presentation, and you answered this question because you explained very well.
It's okay, but I will answer it again. Why do we use greedy when dynamic always works? Basically, as seen, dynamic uses memoization and tabulation, and these both techniques solve the problems very perfectly. But as seen, they work in linear time. Its time complexity is big O of n. And the greedy approach, when we are using a suitable data structure, which is a balanced tree, we get a more efficient and more optimal time complexity, which is a logarithmic one, big O of log n. And therefore, in some use cases, when respecting the limitations that I mentioned, greedy algorithm works best and better than dynamic programming, basically. Yeah. I hope this answered the question. If not, feel free to reformulate it.
I hope so. And other question was about recording video, but I sent a link. Yeah, I'll share this video a few hours later today, so tonight. So, okay.
Very nice. Okay, yeah, he's satisfied with my answer. That's nice.
Okay.
Yeah.
So,
Yeah.
okay, it brings us to the end of today's session. Yes.
Yeah. This actually was very brief. I wanted to keep it light since it's Sunday and, well, 20 people are here. That's already a nice commitment. Thanks for showing up. And
But the explanation was perfect.
yeah, thanks. Yeah,
As always.
quality over quantity.
Exactly.
Yeah,
So,
yeah.
thank you
Thank you so
all for
much.
your participation. And of course, remember to submit after event form. This helps us to make next sessions even better. And of course, once more time, thank you all for joining. We're looking forward to see you in our next sessions next Sunday.
Yeah,
Biggest
see you
thank.
in our last session, basically. Yeah,
Yes.
yeah.
Okay.
Then, bye. Ciao.
Ciao.